Hello, my name is Rory Fulgier and I am the Pre-College Education Programs Manager at Wolfram Research. And today we're going to hear from a few different groups and presenters from our student teams. So some student ambassadors, some students who've gone through our Wolfram Emerging Leaders Program, and some students who've been through the high school summer research program before that. And we're going to hear some presentations on a variety of topics. We've got 3 presentations today, and we'll get through those, and then we'll have any questions that people want to ask. You can ask those at the end of every presentation. As is common for this kind of thing, it's going to take just a second for each presenter to set up their camera and microphone, but that's okay. We don't need to worry. And we are going to start out today with Pragyan is going to be our first speaker.
So I'm Pragyan Yadav. I did the Wolfram High School Research Summer Camp last year, and I'm currently a Wolfram Ambassador. And I'm also an undergraduate student at the University of Connecticut. And I'll be presenting my research on exploring solar complexity by analyzing the solar images. So the main part of this research is just understanding and trying to build computational tools and understand solar complexity through observational data. So go over the outline. Basically, I'll go over the introduction and motivation, the introduction to the problems of solar physics that I'm trying to tackle through this project, and the motivation and why they're important to solve and how we can solve them. Then I'll go over the inbuilt resource functions for collecting solar data that are already built into the Wolfram language. And then I'll talk about the feature segmentations of segmenting important features from solar images, which are really important to analyze and will be really useful for down the research. Then I analyze these features through this measurement I call fractal dimension. I'll lay out what exactly I mean by that and how I calculate that in this project. And then I'll just talk about how I use this fractal dimension to analyze these solar features and try to understand the complexity of these features. So for an introduction, there are many long-standing problems in solar physics, but one of the main ones right now is trying to understand solar flares, so their buildup and then their eruption. And solar flares, and there are 2 parts to this problem. One is trying to understand the physics of how to model precisely these flares given initial conditions and how they erupt and how intense these flares are. But the other end is trying to understand how we can predict these flares for our engineering and space missions. And these 2 problems are really closely connected. So the biggest clue we have of trying to solve this problem is the immense and large amounts of data we collect through our satellites. So currently we have numerous satellites orbiting the sun, collecting data, and I'll be focusing mostly on the SDO, the Solar Dynamics Observatory, which takes immense data at like 12 seconds, at every 12 seconds of the sun, in different frequencies, and also collects magnetic data. And this data is really important to extract, so we can take this data and then apply our computational approaches to it to extract new insights from this data. So the Wolfram language already has great support for solar data. As you can see, there are a lot of different frequencies and satellites to which we can acquire solar data inbuilt already into the Wolfram language as a resource function. These are just some of the images that I use in this project, which are from the Solar Dynamics Observatory. And then we can also take images from, say, time t1 to time t2 and then plot them as a video, something like this, which is quite beautiful and fascinating to look at. And then we can also get the X-ray flux or the soft X-ray flux, which is considered by most solar physicists to be a measurement of how intense a solar flare or solar storm actually is. And we can plot that for any time t we have. So we have this immense data, but what can we actually do with it? So what I do is I take magnetogram images from the STO satellite. Now, magnetograms are just images that show the magnetic field of the sun. So this is a small cutout of a region. This is a better example of the full disk sun and the magnetic regions of it. And so if you can see, the white regions correspond to the positive polarity regions, and the black regions are just the negative polarity regions. And all the gray you see is just weak magnetic fields. So using the Wolfram language, we can easily segment out the positive and negative polarity regions, and for small cutouts, and also for big full disk images. But then the main feature that we're really interested in magnetogram images is called the polarity inversion line. And the polarity inversion line is just this region between the positive and negative polarity regions. And all this region does is, this region is really important for understanding solar flares, because it has been established in solar physics that these are where flares erupt from, this vacuum between the positive and negative polarity regions. So it's this region right here, between the positive and negative, and then this region right here too a little bit. And then I developed this 5-step method or algorithm to extract and segment out this polarity inversion line. And then we can do the same for extreme ultraviolet images. So this is looking at the sun in a different frequency. And if you see, the bright regions in the sun are called the active regions. And these are really interesting because they have really intertwined magnetic fields and really interesting characteristics about their plasma and magnetic fields. The other really interesting region is called the coronal holes, which you can see right here, or the darker, more cooler regions. And they too have really interesting magnetic fields that we want to study and have found to be correlated to solar flares and CMEs, coronal mass ejections. So we can extract out the active regions by just applying a simple threshold and then binarizing it. And then we can extract out the coronal holes by first getting rid of this outer black region and then applying a threshold to mask out the bright regions so that we can just get the darker regions. So, okay, we have all this data, and then we have all this processes to extract out regions from the sun. But what can we actually do with them now? So one measurement I use is called the fractal dimension. And the core idea of the fractal dimension is summed up by this quote by Mandelbrot, the father of fractals, which states that clouds are not spheres, mountains are not cones, and coastlines are not circles. Essentially, the core idea is that you don't ignore the roughness or complexity in given observational data, but you actually embrace it and look directly at it and measure that. So the fractal dimension, so like dimensions in common mathematics, for a point is 0, for a line segment is 1, for a square we have 2, and for a cube it's 3. But here we have dimensions between 1 and 2, where you don't exactly have a line, but it has properties, has area-like properties. So if you see this common fractal known as the Sierpinski triangle, the dimension is between 1 and 2, because it's not exactly a line segment or a line, but if you zoom in, it has area-like properties, but if you zoom in, it is just made up of line segments all the way down. So this occupies a space between 1 and 2. Now, the way I calculate my fractal dimension is called the box counting method, and this dimension is called the Minkowski-Bouillon dimension. And the way the box counting method works is very simple. You just project your image onto a grid, and then you count the number of boxes it takes to measure up the outline of your image. So this example is a really common example for fractal analysis. It's called the coastline of England, Britain. And so we can find the number of boxes it takes to get the outline, to cover the outline of your image. And then you just decrease the size of the boxes, and you keep doing that. And to the relation of the size of the boxes and the number of boxes it takes to cover up your whole image, we can find the fractal dimension. And the way we do this is just plotting the log of the number of boxes it takes to cover up your whole image and divide that by, and then just find a slope with the box size. So here I take a magnetogram cutout and plot the fractal dimension linear plot. But if you can see, it's not exactly fitting a linear plot. It is slightly quadratic in nature. And so if I plot the residual plot of this, we can see that it's a clearly parabolic structure. What this indicates is that maybe magnetograms, or the magnetic field of the sun, doesn't just have a monofractal property, but it is actually multifractal in nature. And this is really interesting because this indicates that it has different levels of roughness or fractality at different levels as we zoom in. And this also holds up for full disk images as well as cutouts. Now, before we fully analyze these images, we should just set up some cautions. So one is the image resolution and thresholding. And the idea is that if you make the image more, if you have a higher resolution image, you can access more of these fine-grained details. And then we can have a higher, we can capture more of these details, capture more of the roughness and complexity, and get a better idea of the complexity. And so then our fractal dimension also increases. So this plot just shows that as we increase the fractal, we increase the image resolution, our fractal dimension also increases, which is important to know before we compare our data. And same with threshold. If you apply a higher threshold, we lose that complexity, we lose that roughness, and then our fractal dimension decreases as we increase that threshold level. And these are just important cautions to know before we dive into actually comparing our fractal dimensions across images. Then I analyzed two images. One is the polarity inversion line in magnetogram images. And what I find is that I bin them by the intensity of the flare that region generates in the next 24 hours. And what I find is that the bigger your polarity inversion line is, the more intense your flare gets. So class X is the highest class, the most intense flares that you've been seeing quite often this year now. And then M and C are just a tier lower than that. As you can see, the more intense your flare is, the bigger your area gets. We're just plotting area on the Y. But then interestingly also, I found the fractal dimension of the PIL area, the polarity inversion line area. And what I find is that the bigger the polarity inversion line, the more rough and complex it gets, the higher the fractal dimension as well, which is an interesting result because this indicates that the bigger the polarity inversion line gets, it intertwines the magnetic fields more, and there's more magnetic activity going on, which is interesting to know. And then we can also find the, then I find the fractal dimension binned by the flux intensity. And this is an interesting result because what I find is that as we increase the intensity of the flares, our fractal dimension gets lower. And then my hypothesis for why this is happening is that maybe the polarity inversion line gets less complicated, less twisted. It simplifies just to build up to a more powerful flare. So it loses that complexity, that magnetic and plasmic complexity that it once had, to simplify down so it can erupt a bigger flare. And then I find interesting results for active regions, which are just the bright regions in extreme ultraviolet images. And what I find is that similarly, the active region, the bigger the active region is, the more complex the fractal dimension gets. And I find a similar result with the coronal holes as well. And this this research just shows how we can use computational approaches or the Wolfram language with symbolic and functional paradigm to extract new insights from already existing data. And then I guess one really interesting future work we can do with this work is try to predict solar flares by their fractal dimension, which seems to be a key property of these features and a unique property too. That's all I have. I would love if there are any questions that I can answer.
Fantastic. Thank you so much.
Great.
Yeah, if anybody has any questions, that would be really great. Feel free to come on to the Q&A or the chat. But when you were doing this, what were the kind of really big things that you learned? What did you get excited about?
I think like one of the really cool things is just that like how easy the Wolfram language is to, if you set things up properly, how easy it gets to really like if you set up the proper pipelines of like having your data and then analyzing and then like pre-processing it and all that, it becomes really easy to just like get the final results down. But if you don't have that foundational work done already, then it gets really hard to do more computational stuff. It's just like building a stack of like tools, which I find to be really interesting.
Very cool. Awesome. Well, thank you so much. This was really great. Really appreciate your time.
Thank you.
Rory, Jeff had a comment on the Q&A.
Oh yeah, Jeffrey says this should be presented as a community post with all the intermediate code. I agree. You should write a good community post about it.
I was planning on doing that. Yeah.
Yeah, you should definitely do that
this month. All right. Thank you. Yeah.
Very cool. Okay, fantastic. So our next speaker is Monsinos, and he has prepared a video with his research partner for us to watch.
Hello, our topic is an analysis of colloquialisms, Spanish from Mexico and Spain. We are Jefren Kostiuk and Jesus Adrián Montesinos Correa. A brief introduction. This information was taken from the Wolfram database. The language we have focused on is Spanish. Why? It's one of the most spoken languages in the world. We can count up to 5.38 million people, but the number of native speakers is just 4.63 million people. So there is many people learning Spanish, but what are the top 5 countries with the most speakers? The first place is Mexico, then Colombia, United States, Argentina, and Spain. So this leads us to the motivation of our project. There are many dialects of Spanish. For example, Mexican Spanish, Northern Peninsular Mexican Spanish. Many of these are from Mexico, as you can see. So what's the ratio, Mexican versus others? Here, we can see that 1 out of every 4 variants of Spanish is from Mexico. So we decided to focus on a specific type of words, colloquialisms, that are informal words or phrases used in a casual conversation. We want to answer one main question: what are the distinctive features of the colloquialism? With this information, we will be able to answer if it's challenging to comprehend the colloquialism of the other variant, or if we can guess the variant of the colloquialism. The data was colloquialism from podcast, books, personal experience from different contexts. The main challenge was to get the equivalent colloquialism, given that they could have multiple meanings. The analysis, we just got one-word colloquialisms to avoid this more hard, but a similar analysis could be done in multiple word colloquialisms. So first we import the data, and then, for example, this is one example. The Mexican expression is estar padre. Expression from Spain is molar. This means this is really good. First, we get the length of the words and the average. Here, we compare the length of the same colloquialism, the dots, and then get the average, the line. So here we can see that Mexican colloquialisms are longer than colloquialisms from Spain. Letters on each word. To, to do this analysis, first we defined a function to remove the special cases. So as you know, in Spanish there are some accent marks, and then we remove them to get just a single variant. This was done with the function clean that lowercase the word and then remove the diacritics. Here we just are applying the function, counting the letters, getting the letters, and we can see that there are different letters, even given that we have around 20 colloquialisms. This was unexpected because there are enough words that maybe we can have the same letters, but now there is something different. Maybe if we collect more words, this could change. With this analysis, we want to understand what's the frequency of the letters, the common letters, the unique letters from Mexico, and the unique letters from Spain. First, the common letters. The common letters are these, and this is the plot. So we can see in this plot that D, G, O, T are equally distributed, but A, C, H, R, U, V are more common in Mexico. E, L, S are more common in Spain. So this is interesting because there are more words unique in colloquialisms from Mexico and Spain. So what about the different letters? They have a similar behavior, right? For example, the unique letters from Mexico are B, F, M, N, Q, and from Spain are J, P, Y. So it's almost the same, right? There are more unique letters from Mexican colloquialisms than Spain, and also the distribution is different. We got the distances between the corresponding colloquialisms between the two variants, and we can see that some variants are really similar, but some of them are completely different. So it could be a little bit hard to guess the variant or the meaning of the word. Here, we are going to see the relations between words. For example, Spanish from Mexico has this kind of relation, right? So here, for example, if you know this word, you can understand a little bit more this word, and with this word, this other word. So this relation is interesting, and also there is a word that is unique, right? That you cannot deduce the meaning of the word just by looking other words, but this is unique. Relations from Spain, the letters are related, right? It is not like Mexican colloquialisms that there is a single word alone. No, this is are related. So this is interesting to see how the relations are in this context. And to finish, our conclusions are a colloquialism could have many equivalences. Yes, it is not always one-to-one, And this is something hard because sometimes you need to, well, we needed to select the most accurate translation, not the most accurate equivalent from Mexico and from Spain. Colloquialisms from Mexico are longer and they have more letters than colloquialisms from Spain. According to Demerau Levenstein, this tense, there's a complete different ways to refer to the same thing. And it's possible to guess the variant of the colloquialisms given that there are unique letters belonging to a specific variant. This could be a little bit challenging, yeah, because maybe you need to be in context to understand this. But if one clue, it is the number of the letters present on each variant. So this was our presentation. Thanks for your attention. See you.
Hello.
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 Hi, how's it going? So, yeah, Colin, it looks like maybe you have a question, although, okay, so Colin's asked to come up and speak, so let's see if Colin would like to ask his question out loud. So,
can you hear me?
yeah.
Thank you.
Yes.
Maybe a live question regarding this is basically difference between two dialects. Spanish is spoken in both Spain as well as Mexico. I would be more interested in having this between two similar languages like Spanish and Italian or Spanish and Portuguese. Thank you.
Okay, yeah, totally. So I think the question at the end of the day is, are you planning on kind of extending your work into analyzing in similar but different languages? Like Spanish and Italian, rather than, like Mexico and Spain both speak Spanish. You're muted, by the way, Monsinos, you're muted. We can't hear you.
Can you hear me now?
Yep.
Sorry. Yes, even that, for example, when you speak Spanish, you can understand up to 4 more languages by 80%. It's Portuguese, Italian, French, and another that with a weird name. So yeah, there are some variants, and maybe that could be our next step. We focused on Spanish from Mexico and Spain. Well, because I am from Mexico, my first language is Spanish, and we had this idea. But yeah, I think that extending this analysis to another similar languages could be nice. Or one of our ideas was, for example, I did this work with Jevin Kostiuk. He is my professor. His first language is neither Spanish nor English. So we had an idea that, for example, what are the unique, how can you recognize if I am talking to you in Spanish or English if neither of them is your native language? So answering your questions is yes, we are going to try to do this a little bit more interesting to other languages too.
Great, awesome. Thank you, Monsinos. We really appreciate you coming in to give us this talk.
Yeah.
Thank you.
See you. Thanks.
Okay, and then our final presentation is a nice little collab between Tyler and Andrea.
Okay, cool. So our project was on bringing Monte Carlo research into the Wolfram language. Just a little bit of introduction. I'm Andrea. I'm a freshman at UC Berkeley, and Tyler and I have both done the Wolfram Summer Research Program in 2023 and TA'd just this summer.
Yeah, and I'm Tyler Rose, senior at Monte Vista High School. Okay, so we develop a general framework for Monte Carlo tree search. on 2-player board games and evaluate its efficacy by conducting comparative analysis on the use of varying time constraints, selection functions, simulation methods, and neural network integration.
So just a little bit of overview on what we'll be covering. We'll start off with a little bit of background and kind of motivation for what Monte Carlo tree search is and some potential use cases. We'll move into our implementation, and then we'll do a little bit of analysis on our algorithm's performance, and then show off some functionality with integrating with neural networks.
So some background. In 2016, AlphaGo beat the 18-time world champion Lee Sogol in Go, which is a very historic moment in AI. And the secret weapon behind this was Monte Carlo tree search. So Monte Carlo tree search is a powerful heuristic tree search algorithm for decision-making in complex environments. It's been used for game AIs like chess, Go, and poker, robotics, planning and scheduling, and even finance and portfolio management. It can be combined with machine learning for even better, more powerful results. So Monte Carlo tree search is a Markov decision process, which is essentially a mathematical framework for decision-making under uncertainty. It uses reinforcement learning, which means it improves from experiences. And the key feature is that it balances exploration, which is trying new options, and exploitation, which is using existing known good strategies.
And so Monte Carlo tree search can be divided into 4 main phases: selection, expansion, simulation, and backpropagation, which we'll talk about more in detail later. So our main goal with doing this was that we wanted to develop a really general framework for Monte Carlo tree search that can kind of accommodate like any variation of Monte Carlo tree search and any applications, so different games and other applications. And so within this, we wanted to analyze kind of scaling laws of different implementations, compare their performance, and end up developing an optimal usage strategy.
So moving on to implementation. So we go for a state-based approach, which is different from certain other approaches, but this is basically for simplicity and ease of use. So states are represented as a simple association where you have a player and the state, which can be basically any data type. So the tree itself is represented as another association where you have a graph object, which represents the associations or the connections between all the nodes in your tree, the current state, and visits and scores, which are associations where states point to integer values, which contain the score and visits values, and the next best state. So here are some examples of what the Monte Carlo tree search representation looks like. So the first stage is selection, which is essentially choosing promising nodes. So essentially, each node has a value, which is the estimated quality of the node, and the selection function contains an exploration constant, which tells it how much to explore less visited nodes. So the node values and exploration are used together to select nodes. So the key behind this is what's called a UCB function, or upper confidence bound for trees, UCT as well. These functions essentially balance exploration and exploitation through a simple mathematical expression. So given the value of a node, the number of visits, the parent visits, and an exploration constant, it'll rank each node, and then based on that, we can choose which one to select. We also implemented what's called prior probabilities. So for certain games, before even playing the game, you'll know information about it, knowing that certain moves are good, certain moves are bad. So you're able to essentially weight certain nodes, give more bias towards certain nodes before playing the game. And through prior probability functions, you can incorporate that information into the Monte Carlo tree search function.
Yeah, so the next phase is expansion, which is just the process of adding new nodes to the search tree. And this phase relies on a user inputted iterator function. So an iterator is just any function that takes a state as an input and kind of outputs all the possible subsequent states. So in the context of tic-tac-toe, you could give it the initial game board, and the iterator would return a list of all the possible first moves.
So the next step is simulation, which is essentially determining or estimating the value of a newly expanded node. And the way this is done is through random rollout, or essentially from the newly expanded node, you play a full game until you get a result. And then based on that result, you can update the values of all the nodes that led up to that node. And the rollout function is essentially user provided. Yeah, sorry, go ahead.
Okay, and then final phase is backpropagation, which based on the results from the simulation phase or the rollout, the visit counts and score values for all the nodes in that path are kind of updated accordingly. So an example is in like a 2-player game where you're alternating turns. Let's say our simulation returns a win for player 1, then all the player 1 nodes in that path would be rewarded. All the player 2 nodes in that path would be punished, and then the visit count is incremented for all of them. And so one kind of functionality that's specific to our backpropagation is that we ended up choosing to update. So for nodes that have multiple parents, we update all of the parents as opposed to only the one that was visited during selection phase. And the logic behind this is kind of just hoping to have the tree learn more quickly by giving it more information. Yeah. And so moving on to analysis, this is kind of the metrics we use to like measure how well our algorithm is performing. So given that tic-tac-toe is like supposed to be a tie if both players play perfectly, one way to measure this would be measuring the tie rate versus a minimax algorithm, which is basically a perfect player. And so as you can see in the top 2 graphs here, we plot number of iterations where each iteration is going through all 4 phases, and then or like time goal, which is how long Monte Carlo has to make a decision. So we plot both of those against the tie rate versus minimax. And so every data point would be 30 simulations of random, or not random, but 30 simulations of games. And then we would measure the tie rate. And so something we can take away from these 2 graphs is that as Monte Carlo tree search gets like infinite iterations or infinite time, its performance approaches that of a perfect player. And then if we look at this graph on the bottom, an alternative way of measuring its performance could be looking at the Monte Carlo search tree itself as opposed to individual simulated games. So here we would kind of take a look at the best next move at every node in the tree and then mark it as kind of correct if it matches minimax, incorrect if it doesn't, and then tally from there. So we have 3 different statistics. You have the proportion unvisited, which is just how much of the total game tree that our search tree has seen. We have incorrectness rate, which is like how often the next best move Monte Carlo tree search gives is correct based on the ones it has seen. And then we have overall incorrect rate, which combines both. And it gives you the number of correct decisions out of the entire game graph, and like stuff that it hasn't seen is counted as incorrect. And so another thing we can notice is that as iterations goes towards infinity, our incorrectness rate and stuff that hasn't been visited tends towards 0. Another thing we looked at was the exploration constant. This gives a little bit more intuition behind what exploration constant is, but we can see as iterations grows, and then we look at the proportion unvisited. So for an exploration constant of 0, we notice that we don't explore the tree at all, and so 100% unvisited versus like a high exploration constant like 5, we would explore more of the tree. And so kind of using this to measure like what the best exploration constant would be, we noticed that if we look at overall incorrectness rate, it's heavily correlated with how much has been explored. So the exploration constant of 5 is still the best, but maybe more accurately, we can look at the incorrectness rate of just what part Monte Carlo tree search has like seen already, and we can see that it varies for different numbers of iterations, but generally this green one seems pretty good, which is exploration constant of 2. We also looked a little bit at UCB functions, and we noticed that UCT or PUCT seems to do the best job exploring the entire search space, and then kind of which function does the best at actually making the decisions on incorrectness rate also varies by the number of iterations. Yeah, and this just kind of summarizes what I mentioned before.
Okay, so moving on to neural networks, we essentially replace certain parts of our of the algorithm with neural network-based models. So the problem with random rollout is that it often takes a long time to run because you have to run a full simulation of a game. And with neural networks, you can basically perform inference just instantly, regardless of how deep the game graph is. So in order to train a neural network, we first basically gathered some data. So the data set we used was essentially just from Minimax. So perfect play on a tic-tac-toe. And obviously this is a scaled down case, but in theory, you could scale this up to like a bigger game like chess or something like that. And then, yeah, so for the model, we basically initialized a fully connected neural network and then trained it on a proportion of the data set. So obviously you can't, if you train it on the entire game tree, it would just memorize all the best moves. So we trained it on a subset of the game graph, so it would have some generalization. And its accuracy ended up to being 93.6%. So then we basically just evaluated it against normal Monte Carlo tree search. So using the neural network as the simulation function versus using rollout. And it had a much higher win rate running for the same number of iterations. And it took less time to run by the 2 bar graphs there. So yeah, overall, it was a lot better. So we basically, in conclusion, so yeah, we developed a Monte Carlo tree search framework, and we analyzed time constants, UCB functions, iterations, exploration constants, and we successfully integrated it with neural networks, which was very efficacious.
Yeah, so thank you for listening. We're happy to take any questions.
Fantastic. Well done. Great. I really appreciate your work. This looks very, very cool. Yeah. Okay. Fantastic. Tell us what the biggest thing that you learned during doing this project was.
I guess I can start. I feel like it was really I thought a really interesting part was like I've done a little bit of stuff with like different game graphs before, but this is kind of the first algorithm that would work where you don't have like perfect information. So in theory, this algorithm would be able to work with something that has like dice rolls in the game or like some element of luck or some element of like human bluffing. And I just thought that was like really cool that we're still able to kind of extract like what a better move would be with a computer, even when we don't have like super certain circumstances.
Yeah, so for me, I came into this project with very little knowledge on like game graphs and game theory and all that. So this is my first real like interaction with the field, and I had always wondered about things like AlphaGo and AlphaZero because like my machine learning experience isn't really close to that because I hadn't done much like tree stuff. So learning Monte Carlo tree search and seeing how you can integrate like deep learning models with it to make it even more powerful was really interesting to me. And like I enjoyed coding it all up and all that with Andrea.
Great. Awesome. Fantastic. Okay. Okay, thank you everybody so much for listening to our students. They do some wonderful work. Most of these students are part of the Wolfram Student Ambassador Program, which is a great opportunity for people in high school through postdoctorate study, working on a bunch of different projects. We support you to write your own research papers and essays and speak at various different conferences, and it's a really great opportunity for anybody in that kind of stage of life. We really enjoy having people. You can find out more at the Wolfram Student Ambassador Initiative website, which is easy to access if you type Wolfram Student Ambassador into Google. It's the first one. And if you have any students that you're associated with who you think would be a great fit for that program, feel free to send them the link. We always love having people getting involved. Okay, that is it from us. Thank you so much for coming. We really appreciate your time and energy, and I hope you have a great rest of the conference. Thank you, everybody.